Thank you very much. It's very nice to be here. Thank you very much to the organisers for having me. For the last, it's actually, oh gosh, how long is it now? Almost 15 years I've been involved in this rather ridiculous artistic performance practice, which is writing musical compositions in code in front of an audience and doing all of this on the screen so people can follow along with what I'm doing as I'm going along. So one of the things I just wanted to start with is, if I mention the word live coding and musical performances, and you know what I'm talking about, can you put your hand up, please? Wow, that's pretty good, actually. In fact, that's very good. So that's actually particularly good because today, one of the things I want to do that's a bit different is usually in a live coding performance, you know, obviously you're trying to write a piece of music and you're trying to do that within the time scale of what's normally considered a composition. So obviously you have fairly tight time constraints on what you can do. So the result of that is that most of the things that you're doing are at a fairly high level. You're doing lots of notes and chords and scales and these kind of things, but you're not doing all of the audio synthesis underneath because it would just take too long to build everything. That's not to say, though, that audio synthesis isn't actually happening, because, of course, it is happening underneath. So what I wanted to do today is I wanted to actually start from absolutely scratch and build up a couple of synthesizers for you. We're going to sort of go through this process, slowly building these things up, and then build up a little piece of music for you, but we're going to do it from scratch. So it'll take a little while to get everything going, but I'll try and explain a little bit about what I'm doing as I'm going along. And hopefully by the end you'll have a little bit more of an idea about audio sound synthesis and how all of the mechanics of this work underneath. So this is kind of like the very bottom of the audio stack. This is kind of it's basically a callback coming directly from the audio device, really. And what it's asking for is it's asking for us to return what is effectively a position for the cone of the speaker at some point in time. So with this function that you're looking at here, now, of course, I'm a Lisp programmer, so you know we're pretty fast and loose with the functions, right? So, but we'll get away with that today. So, but what's going on here is the channel. We've got a channel and a time coming in, and time is going to move in series, and we're also then going to move between the left and the right channel because today we're going to be working with this stereo image. So the first thing we've got here is random, okay? And random's going to give us back a number, in this case between 0 and 1. And we can think of this as positive and negative voltages, which are either pushing or pulling on the speaker cone, okay? So let me now turn this up a little bit. This 0 here is effectively working as a gain. So I'm going to compile this in. I'm going to turn this right down because I'm not sure how loud this is going to come out. Hopefully everything's still connected. Everybody feeling very seaside-y at this point? Okay, so now, of course, we can change the gain directly here. Okay, and I'm just changing it on my device as well. I'm going to be mixing backwards and forwards today. But at the moment, what's happening is this white noise is basically just random numbers moving the speaker cone. And you're hearing that as white noise. But at the moment, this is a unipolar signal. We really want it to be bipolar because we want negative as well as positive. So let's just abstract that out into a noise. And what are we going to do? I'm going to want something like this. And now we can replace noise here. And now we've got bipolar. So now we're getting the negative and the positive coming out. And this is about the simplest, possible DSP process that we can think of. Now, the next simplest thing we can think about is that I'm going to introduce the idea of an impulse, which is basically just, in this instance, we're going to be talking about a unit impulse, which is basically just firing a 1 and then all zeros. A 1 and then all zeros. Okay. So let's see what happens when we introduce this. So we're going to say a delta for our impulse, and then our impulse is going to be some rotating frequency. So let's start that off as 10,000. Okay, so we can hear these pulses, and this is basically just pushing the speaker. Now, the interesting thing happens when we start increasing the rate of these pulses. Okay. So as these pulses get closer and closer together, we stop hearing them as a kind of a rhythm and we start hearing them as a pitch. And that really is the only thing that distinguishes a rhythm from a pitch. So this gets a bit more interesting if we do a couple of these things together and you hear them as a rhythm and then we're going to change them into a pitch. So let me show you an example of what that might look like. So now we've got this rhythm here, okay? So now what we're going to do is we're going to start to speed this rhythm up a little bit. Now I'm also just going to put our gain back in here. Okay, now how do we shut the whole thing up? Of course we give it a gain of 0. It's all quiet. Okay. So now we're going to start building our first instrument, and we're going to use this principle to do a really simple and old style instrument, which is a plucked string algorithm. And basically this is kind of a physical model of a string. So the way this is going to start is that we're going to introduce the idea of a wavetable. So let me push this in now. We're going to say, now the wavetable is going to be the same lengths, the same durations we were looking at for our pulses. So where we were just having these tick, 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 we're now going to have the same kind of interval for our wavetable, and it's just going to loop around. So for our pipe, let's say we want to start this at, I'm actually going to divide it by sample rate, which is a second. So let's say it's going to be a frequency of 200 and noise. We'll also give this an amplitude. And now the first thing we're going to do here is that we're going to get a value from what is essentially a queue, because we're going to fill this queue up, then we're going to pop something off the queue, and then push something back on the queue again. So we're going to pop from the wavetable, and then down here we're going to multiply by the amplitude, so we can have a gain, and we're going to push what we've just popped back on again. Now the interesting thing that's happening here is we're actually listening to white noise again. This wavetable is actually just white noise. But our ears are really sensitive to this frequency, right? Because it's shifting through this wavetable at the same rate, because we're popping and pushing, we get this cycling, which is what gives us the frequency. So to make this the plucked string algorithm that we want, what we want to do is we're going to do this trick that we're going to filter the noise over time. So that's basically going to take all the high frequencies out of the sound, and it's going to do that quite rapidly, and we'll get this interesting sound. Hopefully you'll hear that this sounds a bit like a plucked string. So how are we going to do that? Well, the first thing we're going to do is we're going to introduce a little bit of recursion in here, and we're actually going to do the simplest low-pass filter in the history of low-pass filters. which is literally just an averaging of the signal. Okay? Simple as possible, but if you think about it, it's fairly simple to understand. I mean, basically we're smoothing out the signal, and of course as we're smoothing out the signal, the first things that are going to drop are going to be the high frequencies. So when we compile this in, and of course we can change the frequency of this. Okay, so now what I want to do is I'm going to make a little player function so that we can actually, play these things. So let's just drop down. We're going to set that up down here. We're going to play the string, and it's going to take a pitch. It's going to take an amplitude, and we're going to set the wavetable to be separate. I'm going to use, the reason I'm using pitch to frequency here is I'm going to use kind of pitches from a piano rather than frequencies, just to make life easier for myself. Audio pipe, and of course we need noise, so we'll pass in the noise, and then we need the amplitude. So we can pile this in, and then we can call play string. So 60 is middle C, basically, middle C on the piano, and we can go down from there and up from there. Now, at the moment, we're actually moving through, this is actually an octave higher than it should be, because we're moving through this wavetable really at twice the speed we should. So we're actually going to do a bit of a, well, not a cheat, but we're just going to repeat here. All right. Okay, so now I'm going to put this in a little loop so that we can start playing a little melody, right? A little riff. So here we go. We're going to call this riff, and make it my third. Let's start with 60. This is going to be the simplest little riff of all time. It's a riff I use a lot, actually. I kind of like it. And we're just going to say if the pitch is 60, pass back 63, otherwise 60. And we just need to call our play string. We're going to pass in, what do we need? The pitch and the amplitude. I'll turn this down a touch. Actually, let's make that quieter. Okay, now I'm going to change the volume a little bit because it's just constant at the moment, but I want to give it a little bit of variation. So let me change that. You know, I have no idea what's going on with that. Anyway, it's just changing levels on me. So here we go. So what I'm going to do is, let's make this 4.2 and 2. I haven't, when I eval, you'll see it flash, and you should start to hear it kind of, rather than this flat, it should start pulsing a little bit for you. So you can hear it's kind of got a little bit of a groove going on now. Okay, so let's just stop that for a sec. So the next thing I want to do is I'm going to do a cheat here. We could do, I mean, of course there are nicer ways to do this, but what I want to do now is I want two of these, because I actually want one coming out of the left speaker and another one coming out of the right speaker. So we could do it properly, but I'm not going to. I'm just going to copy and paste. And we're going to call this string sound. We're going to call it 1, and we're not going to need the repeat anymore. Damn, I did my copy and paste too early. So now we need string sound, and we need string sound. Okay, so we'll compile this one in, and we'll also call this string sound 1. Actually, I'll just delete all this and copy again. Go up, call this 2, call this 2, 2 and 2. And now what we're going to have to do is we're going to have another sound, right? Because we just got rid of the one we had. And like before, we're going to have an amplitude just to globally change things. But now we're going to put in a little conditional here for the channel. And so based on this conditional, we're then going to either use string 1 or string 2. So let's go string sound 1, which takes a, what do we need? Time and chan, of course. And string sound 2, time and chan. And we'll multiply all of that by amp. Now, when we play the first play string, we should be back to where we were, but you should only now hear it coming out of the left speaker. So let's start that off again. The right speaker. Now, interestingly enough, if you listen, you can actually hear the hum of the other one out of the left because it's always resonating just very softly. So let's introduce the second one now. And for this one, what we're going to do is we're going to push it up a fifth. So the 7 is a fifth in musical terms. And I'm also going to sort of go on the opposite. So instead of being the 60, so we'll always go the opposite to what the other one's playing. And let's change from a cos to a sine. So we have a phase shift in where the pulsations are happening. Now we'll introduce, and we need that to be string 2. So now we've got the 2 different instruments, basically. Oh, and something I should have mentioned, sorry. Well, no, we'll get to that in a minute. Okay, so now we've got some instruments playing, but it's very dry. Okay, can everyone hear me over the music? Yeah. So it's very dry. And that's because when we speak in a room like this, you know, we get reverberation. Now, my voice is hitting all of these walls and it's pinging off all of these walls. And in a very simplistic sense, those are just delays, okay? It's just the time it takes for my voice to hit that wall and reach your ear as opposed to coming directly to you. So we're not going to do a full reverb, but what we are going to do is introduce a little delay effect for these instruments. So to do that, we're going to... I'm just going to start, we'll do one channel at a time, so you can kind of hear the effect on one channel and then we'll copy it across to the other one. So we're going to grab the signal that's coming from the first string, and then we're going to use an extempore function, tau, which is basically just a delay. It's going to take the signal that's coming in and it's going to offset it by some number of samples. And here what I'm going to do is I'm going to say delay time left, and I'm going to make that SR here stands for sample rate. It's the number of samples per second we're processing. You can think of SR as 1 second, basically. So we're going to divide sample rate by 4. So 1/4 of a second is going to be our delay time. And so I'm going to delay and delay by DTL. And then we're just going to add, which sums or mixes our 2 signals together. So now, when I compile in sound, you'll hear both the immediate signal coming and the delayed signal, just in one of the channels. So you can hear it over here. Can you hear that delay now? Now at the moment it's only doing one delay, and what we'd really like is to also have feedback, so the delay keeps on sort of cycling around as it goes. So let's just introduce a little delay here, which is actually going to be the delayed signal by some feedback. Okay, so I'll stick feedback up here so we can control that, and we should be good. Now, as I turn this up, you'll start to hear the effect of it much more. So I'm just going to change the feedback level here. So we're currently 0.5. So you can hear the feedback going through the delay. Let's cut that back. So now we're just going to copy all of that over, because we're going to use it for string 2 as well. But we're going to have 2 different delay times. We'll have a delay for the left and a delay for the right. How are we looking? Delay right. Delay right. And now we have the delays both left and right. Now I'm going to put one more little change in here, which is that at the moment I want to take the high frequencies out faster so that the string sound kind of dulls a little bit. It'll sound a bit more like it's being plucked close to the bridge of the string and also with a little bit of a mute on it. So we'll do that here. by making the feedback. So what we're doing here is we're basically just filtering the signal quicker. Okay. What am I doing? That's all good? No. Up here. So let's now introduce a bass line so we can have another instrument going at the same time. And for that, I'll just turn this down for a sec. And for that, we're going to use an FM synthesizer. So FM synthesis is basically frequency modulation. And to do that, we're going to need an oscillator. So I'm just going to introduce a little oscillator here. There's our riff down there, which is going to take a phase. It's going to need an amplitude and a frequency. Oops. And what are we going to do? We're going to increment the phase by... Now we're going to need... Let's define a global value for this. It's just going to be 2 pi, because we're going to need the oscillator to be a sine. In this case, we're going to use cosine wave. We just need a sinusoid, so it doesn't really matter whether we choose a sine or a cosine for this. And we're going to want it to be based on the sample rate. And then we're going to multiply that by the frequency. Of course, we need a cosine, and we're going to multiply that by the amplitude. So now we've sort of abstracted out the idea of an oscillator. We can use 2 oscillators for our frequency modulation, because we're going to need a carrier signal, or a carrier frequency, carrier oscillator, and a modulating oscillator. So, back to making a sound. So we're going to go FM sound, which is still a sound. It's going to take a time and a channel. And we're going to have to introduce a couple of things here. We want O1 for our first oscillator, which is going to be our carrier. And then we'll introduce O2 as our second oscillator, as our modulator. I'm going to put a couple of magic numbers in here, which I'll talk about in a second. And then we need the standard things we've been working with, so a frequency and an amplitude. So in the body of our function then, we need the carrier signal, O1, which is going to be our first oscillator. We need to provide it with an amplitude. That's fine. Then we're going to provide it with the frequency. That's fine. But then we want to be able to modulate that frequency. So we're adding that to the output of the modulating oscillator. And for the modulating oscillator, we're then going to give it a modulating or a changing over time amplitude, and the same also for its frequency. And we have an FM sound. So we'll have a listen to this in a second. We need a player for that, like we did above. So we could actually just go up here and snatch one of the players. We'll call this play FM. FM sound. Okay, so now we can make, like we did with riff before, we can start playing this instrument. But before we do that, we have to add it to the main sound routine, because we need to sum it to our signal. So we'll come in here, inside here, we're going to go FM sound, time and channel, same as everywhere else. I'm not going to use a delay on that sound. And now we can introduce it as another part. So I'm going to play this separately to the first, and we'll call it baseline. And this is really just going to run around a rotating list. So we'll call play FM. This is going to be a list, so we'll grab car, and then we need the amplitude and our magic values, which we'll play with in a second. And then inside here, all we're actually going to do is rotate the list. And it's a bass sound, so we need it to be a little bit lower. And here we go. This should introduce our, well, it's kind of going to sound a little bit like a bass guitar. he says, optimistically. Not the best bass guitar I've ever heard, I have to say. What have I done? A, B. Frequency. Foolish. Okay, so we have our bass line playing now. Let me just make a little change here. These aren't actually playing in time because I'm an idiot. So let me change my riff gone. Here we go, right down here. Now the magic numbers start to play a part here, so if we change these you'll start to hear the different kind of timbres that we get out of this FM synthesizer. And one of the interesting things about FM, and one of the reasons it was quite a revolution when it came out, is that from a computational standpoint you can get an enormous variety of timbres out of only 2 oscillators, which of course is a very cheap, well, relatively cheap way of producing a sound, which is why all your crappy sound cards in the 1990s had FM synthesizers in them. And now I'm subjecting it to you once again, so sorry about that. So we have our bass sound now, and what I thought I'd do, now that we've got all this going, I might actually just make one more change. Should we do... No, let's not worry about it. I'm just going to let this play, and what I'd like to do now is I'm actually just going to play out by adding some pre-built stuff so that you can hear, rather than, because of course we built everything from scratch here, right? So, but usually in a performance you're going to be working with a huge library that you've pre-prepared. So I'm going to finish off by adding some pre-prepared goodies to what we've already got, and we'll just take it out like that. So.
Electronic fork occurred within the law
there you have it. So any questions, I guess?
Yeah, can you teach other people how to do that?
Sure. Yeah. Is that a question? Or?
Yeah, sure.
So, I mean, you know, there is actually kind of, so the reason actually for the title of the talk, this idea of, one of the things I find really interesting about working with code this way is that this isn't code for any purpose of production. Right? This is purely code for experiment. So, and by that, everything you're doing sound is a particularly compelling case because you're sitting here, you're changing code, and you're hearing it immediately. So you have a physical connection to what's going on. Of course, sound isn't the only way that this can happen, but sound does afford this kind of capability to use programming languages as a tool for experimenting and learning. And the environment then feeds back and actually gives you this kind of really interesting way to experiment. I mean, this is programming as a science, programming as experimenting in the world. So there's this, subtle kind of idea of, the alchemist, standing there and mixing God knows what into a pot, not knowing what they're going to get out. And in some sense, that's what this is, right? It's about, clearly I'm not pushing things here, but absolutely at home I do. I go, what'll happen if I do this? And then the whole house explodes, But it's an interesting tool. And I don't think, I wish we used programming languages more in that way, as experiments rather than as just slow, as this constant thing about, programming languages are about producing a product. But programming languages are really great learning tools.
Can you explain a little bit more about the stack you're using, like Extempore? What is this? Is it, have you got libraries underneath it?
Well, no, so that was sort of yes and no. So that was part of the point of the talk. So in the first half of the talk, no library, right? The only library that was there is that SND function that you saw right at the start. It is literally a callback from the device driver. Okay, right. So and that also is written in Extempore, but that was it. Now later on, when I brought in the instruments at the end, but for the Plucked stream and for the FM synthesizer, there was nothing hidden. You saw absolutely everything. Yeah. So yes.
Do you have a tool to translate this into more traditional mathematical notation? So for example, if someone knows nothing about coding and wants to read in a pentagram, can you do that?
Yes, no. Sort of. So Extempore actually does have quite a lot of support for doing symbolics. So, symbolic computational work. So rather than just numeric. So no is the simple answer. But you'll also see that, for example, these let R's, which are an unusual construct for a Lisp, okay, if you're used to digital signal processing, for example, you're used to this idea of, X 0, 1, 2, 3, 4 is moving ahead as inputs, Y 0, 1, 2, 3, 4 going back further as outputs. And these recursive definitions, for example, are inspired by that kind of use in DSP. So it makes it much more easy to write, literally look at, for example, a filter and almost transliterate it into a letter R. Now, clearly it's not the same notation, but it can look quite similar.
I appreciate your reference to CIRAC.
Yes.
We're here in Melbourne. Could you explain to
Yes. How many people in the audience have heard of CIRAC? Yeah. So CIRAC was the world's fourth stored program digital computer. Fourth. 1949. It was built in Sydney. It was designed and built in Sydney, and all of the parts for it were manufactured in one way or another in Australia. None of it was imported, which is pretty impressive. And one of the coolest things about CIRAC was that, who would like to take a guess at what year a computer first made sound? And I don't mean being dropped on the floor. So, anyone want to take a stab at it?
Sometime early, like 40s or 60s or...
Yeah, so there's a bit of a competition between Australia and the United States, but the engineers from CIRAC remember it making sound, and by sound I mean out of its own loudspeaker, in 1950 or 1951, which is amazing, right? So right from the birth of the digital computer. The interesting thing about CIRAC making sound actually was that the reason it had a speaker, it had a little speaker cone in the front of its cabinet, and it was used for debugging. And the CIRAC computer actually, its memory was mercury delay lines, right? And one of the things they used the speaker for was actually for debugging these mercury delay lines, as well as more kind of common things like, you know, has a program stopped or started, things like that. But yeah, kind of cool. It then moved to Melbourne in the 19...
CIRAC is at the Melbourne Museum, it's worth visiting.
Yeah, and it moved to Melbourne Uni in late 50s or early 60s. 56. Yeah.
How do you compare and contrast Extempore with something like Overtone? So, please.
So Extempore is my list, my list. The big difference is that in Extempore, all the stuff we were doing there is in Extempore. In Overtone, for example, all the audio signal processing, so all the low-level processing is all being taken care of by SuperCollider, which is a C++ library. So Overtone actually isn't doing any of the signal processing, and it couldn't, it's too slow. So. I mean, I should clarify, I mean, you'd be able to play an oscillator or two, but as soon as you want to do anything complicated.
Do I understand correctly that your callback is being called once per sample?
Once per sample.
So
yeah,
about 20...
Per channel.
Yeah, okay, 20, okay, then about 10 milliseconds per call.
Less.
Sorry, microseconds.
Yes.
Yeah.
So it's 88,200 calls a second.
Oh, okay, oh yeah, much less. Do you have you hit an upper bound with how much processing you can get done in a single call? And
so,
can you tell us something interesting?
About, so this is already running multi-core. So what you just heard is running multi-core. So I was actually running all of the all the early stuff was running on one core, and all the instruments you heard later were all running on their own cores.
Okay, cool.
Yeah. So in Extempore there's no automatic. We don't try and look at the graph and distribute the graph across cores. We basically say to the programmer, keep the graph together. So usually the way somebody will do it is that they'll do it on a kind of an instrument by instrument basis. So a whole instrument goes to a graph rather than trying to split up the actual sort of units within an instrument. But at that level, it's actually very easy. You just go this on this core, this on this core, this on this core.
Cool. And the garbage collector cores won't get in the way?
No garbage collection. So Extempore doesn't use a garbage collector.
Okay.
It uses memory zones, regions, arenas, etc., etc. Many names, but same idea. Cool. We eschew the garbage collector. But I should say Extempore is also a combination of two languages. XT language, which is compiled to native, and it also has a scheme. So for example, all these bind functs are all XT lang, and you'll see it's statically typed, for example. Okay. But the define, so this baseline here, is scheme code. And scheme and XT-lang can call freely between each other. So the scheme code is garbage collector, but the XT-lang code is not. So generally speaking, we use XT-lang code for doing all of our high-performance computing type jobs. And then if we want to do sort of high-level stuff, we can use scheme for that. Although by and large, we use XT-lang for all these days.
So that's something you're aware of as you're using it to make sure that you can...
It is. So how we go for time? So it's interesting actually. So for beginners, it actually can be a bit confusing. So once you're used to it, it's dead easy. But for beginners, the trick is actually that syntactically, it often looks like very much the same. And so when newcomers come to the language, particularly if they're kind of less experienced programmers, they often do get confused because the semantics of the two languages, the syntax can look quite similar, but the semantics is completely different. But one way that we usually get around that is when people are first coming to the language, we just teach them scheme. and they just call into XT-Lang. So they don't build their own instruments, they use somebody else's instruments for a while. But XT-Lang's being used for lots of other things outside of music. We use a lot of high-performance computing, robotics, they're the main application domains at the moment. I do a lot of computer graphics as well.
Cool. Just to extend on some syntax discussion, so interesting domain to try and build it for performance, so trying to keep things readable at the same time as sort of concise so you can write. Can you talk about your journey building Extempore and how you came up with the current syntax and that structure and what you use?
Yeah, I don't know that I can answer that very well. No, it's a really good question. I mean, there are other people in this community who are much more concerned about so it's I think, luckily, I think scheme is actually, it's a really good question because a lot of the performance I do, a lot of the audience don't program at all, right? And what's really interesting is how many people come up to you at the end of performance who say, I've never looked at a line of code, but I kind of understood a little bit about what was going on. Now, the thing that's really interesting is that it's often domain. So if you're writing this stuff and you say, for example, C minor third, there'll be music people in the audience who'll straight away go, oh, well, I know what that is. And there'll be programmers in the audience who go, so as much as anything, it's about choosing keywords wisely. But I think scheme is, scheme's a beautiful language, so I think it speaks for itself in some ways. But there are a lot of other live coders who are more and more looking at trying to get the code to reflect the state of the system at any point in time. I'm less keen on that idea because I think it actually then gets in the road of the program. But it is an interesting one.
Yeah, it's an interesting challenge.
It is. But it's like using controllers. Like a lot of live coders also, because you go, why would you use a cosine to modulate the volume when you could have a mixing desk and do it over there? And lots of live coders do that because, of course, it's trivial to do. You can just have a bunch of patches straight into the code and change the mixing desk. But the problem I have with that is then you type, mix, type, and it's just like, can't do that.
All right. Well, thank you again, Andrew.
Thank you.